everybody ready? Everybody's probably been sitting around for a while anyway. I'll take that as a yes. Hush falls over the crowd. Where to start? For those that aren't familiar with me, my name is Mudge, and I used to run a little organization called The Loft, and we recently merged The Loft into a larger organization called At Stake. A little bit of background about myself. Ryan Russell and the guys over at Security Focus and a whole bunch of other people put out a book very recently, and they asked me to write a foreword for it. And I kind of saw the cover, and I'm thinking somebody might have stepped over the boundaries at some point, because it refers to me as Forward by Mudge, Security Advisor to the White House and Congress. Which, while probably true technically that I did advise them, I don't think I really earned the official title. But nonetheless, that's I guess some people look at me that way. I guess it's a good thing for the country. Well, I guess the best way to kind of give you a little bit of background about why I do what I do, why I surround myself with the people who do what they do and the people that they are, is to read the foreword, which is very short. And in writing the foreword, Ryan approached me and said, "Would you write a foreword?" I said, "Oh, I've never written a foreword for a book before. Do I have to read the entire book? What do I need to do here?" He said, "Well, just skim over some of the parts, see if it looks interesting. And gee, I saw a foreword by Marcus Raynham that had nothing to do with the book, so just go at it." Okay, fine. So my foreword is more of kind of espousing on my personal beliefs than anything else, although I did skim through the book. I'm not affiliated with Security Focus. I'm affiliated with At Stake, so I'm not endorsing. I haven't read through the book, but it looks to be pretty good. My personal belief is that the only way to move society and technology forward is not to be afraid to tear things apart and understand how they work. I surround myself with people who see the merit to this, yet bring different aptitudes to the table. The sharing of information from our efforts, both internally and with the world, is designed to help educate people on where problems arise, how they might be avoided, and how to find them on their own. This brought together some fine people whom I consider some of my closest friends, and is where The Loft grew from. As time progressed and as our understanding of how to strategically address the problems that we came across in our research grew, we became aware of the paradigm shift that the world must embrace. Whether it was the government, big business, or the hot little e-commerce startup, it was apparent that the mentality of addressing security was to wait for the building to collapse and come in with brooms and dustbins. This was not progress. This was not even an acceptable effort. All that this dealt with was reconstitution and did not attempt to address the problem at hand. Now, perhaps this would suffice in a small, static environment with few users, but the internet is far from that. As companies and organizations move from the closed and self-contained model to the open and distributed form that fosters new communications and data movement, one cannot take the tactical repair after the fact approach. Security needs to be brought in at the design stage and built into the architecture for the organization in question. But how do people understand what they will need to protect? What is the clue to what the next attack will be, if it does not yet exist? Often, it is an easy task if one takes an offensive research stance. And this is where the government always goes like, "Don't say the word offensive." Look for the new problems yourself. In doing so, the researcher will invariably end up reverse engineering the object under scrutiny and see where the faults and the stress lines are. These areas are the ones on which to spend time and effort buttressing against. By thoroughly understanding the object being analyzed, it is more readily apparent how and where it can be deployed securely, and how and where it cannot. This is, after all, one of the reasons why we have war colleges in the physical world. The worst case scenario should never come as a surprise. We saw this paradigm shift, and so did the marketplace. The Loft merged with respected luminaries in the business world to form the research and development component of the security consulting company At Stake. The goal of the company has been to enable organizations, blah, 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 corporate stuff. Let's see, where was it? The goal of the company has been to enable organizations to start treating security in a strategic fashion as opposed to always playing the catch-up tactical game. Shortly thereafter, and I thought this was very, very interesting, President Bill Clinton put forward addendums to Presidential Directive 63. And these addendums started showing a strategic educational component to how the government planned to approach computer security in the coming years. On top of this, we've had huge clients beating down our doors for this, so obviously if the market's demanding it, there's got to be some sort of real need. But all is not roses, and while there will always be the necessity for some continual remediation of existing systems concurrent to the forward design and strategic implementations, there are those who are afraid. In an attempt to do the right thing, people sometimes go about it in strange ways. There have been bills and laws put in place that attempt to hinder or restrict the amount of disassembling and reverse engineering people can engage in. There are attempts to secure insecure protocols and communication channels by passing laws that make it illegal to look at the vulnerable parts instead of addressing the protocols themselves. There even seems to be the belief in various law enforcement agencies that if a local area network is the equivalent to a local neighborhood, and the problem in that neighborhood is that there are no locks on the doors to the houses, that the solution is to put more cops on the beat. As the generation that will either turn security into an enabling technology or allow it to persist as the obstacle that it is perceived as today, it is up to us to look strategically at our dilemma. We do that by understanding how current attack works, what they take advantage of, where they come from, and where the next wave might be aimed. We create proof of concept tools and code to demonstrate to ourselves and to others just how things work and where they are weak. We postulate and provide suggestions on how these things might be addressed before it's after the fact and too late. We must do this responsibly, lest we provide people who are afraid of understanding these problems too many reasons to prevent us from undertaking this work. Knowing many of the authors of this book over the past several years, and I basically say these guys all rock. They're pretty cool. They're pretty hip. They've been doing a lot for the community, and I actually think many of them are extremely moral, much more moral than people that I meet on the street or people that politics or government. But with that being said, that is myself. And what I'm going to try and walk you through today is a strategic look at a very common problem. And that very common problem was, how do you figure out when your machine is actually owned? Well, everybody scans looking for known vulnerabilities on the machines, and that's one way of seeing whether your machine has the potential to be owned, but it doesn't tell you whether it's already happened. And you need to look at your surroundings, and when you look at your surroundings, you can see that there are a few things that normally fall into place. You don't have to have absolute positives. You don't have to have 100%. If you get 90%, you're rocking. And one of the first things that they end up doing, or people end up doing when they compromise a machine, is they put it in promiscuous mode. It's a great bang for the buck attack. You take over one machine and you let the standard network utilization and the traffic going by tell you all of the stress points and weaknesses in the area, and then you come back and harvest the information later. And they also put IRC servers on there with egg drop bots, so that's another way of detecting whether you've been hacked. All of a sudden I've got an IRC traffic server. It kind of reminds me of the old, the people who were worried about Satan when that came out. They're like, oh no, you released a tool to the public. This is horrible. Somebody might install it on my system. Yeah, and then you got a free installation of Perl 5 and all the other things you couldn't get to compile. So I approach everything from an R&D stance because I am, the VP of R&D over at this organization, and the previous small company, The Loft, was largely an R&D think tank. And I kind of stole from Douglas Adams' Hitchhiker's Guide to the Galaxy, which is, two important thrusts. One of them is to achieve 3 impossible things before lunch, and then round it off with dinner at Millyway's. But then you need to show other people how to do that sort of work. And this is you need to teach people how to learn. People will always be afraid of proof of concept tools or people putting out advisories if they're just put out in raw data format. Raw data format, it doesn't have a good notion and it doesn't have a bad notion. And as such, you're trusting that the influences around the person reading it are all good and that they're going to do the right thing with it, and this isn't the case all the time. Now, if you put this information out and you put a slant on it explaining or hinting towards a more beneficial use in society, that can make all the difference in the world. But you need to teach people how to learn, and teaching people how to learn sometimes is teaching them how not to be afraid of things. And then the second one is, basically, to regurgitate the line here, it's you have to come up with reproducible results that can be used in a scaling fashion. Little one-offs just absolutely don't work if you're trying to fix the world, or as our internal motto goes, put a dent in the universe. So when approaching something in a strategic fashion, you look at not just the geez, I got hit with the latest virus, I'm going to go get the latest virus signature now. Oops, I got hit with the next latest virus, I'm going to go get the next latest virus signature now. This is after the fact. This is tactical. There's nothing wrong with being tactical, but you're not going to move forward in society if you're tactical. Things are changing. What this basically is saying is that security is not what security used to be before, and the security solutions that people are offering are largely entrenched in the older mechanism, the older model, and this paradigm shift is actually happening right now, and we're seeing it. The paradigm shift being that we're going from an internal to an external focus. You don't own your shipping, your receiving, your inventory. You don't own, you're outsourced to an ASP of some sort. Where the heck are your perimeters and boundaries? You're not worried about sitting there, justifying as an IT security budget, why you need another $1 million. You need to actually sit there and say, I need the next, X sum of money because I can show you some sort of return on investment. How does security play in on that? Security has always been, a cost center, not a revenue generator. Well, we can make it a revenue generator now for enabling companies to do things that they couldn't do before. That you couldn't do without non-repudiation, that you couldn't do without strong authentication, that you couldn't do without understanding and modeling your traffic in the correct ways. And then finally, it's no longer the IT security group that's controlling it. It's the little e-commerce groups. It's the business units that are doing it. So when you're presented with a new problem, you look at new solutions. Sure, you look at the old solutions and see which ones are still applicable, but you don't rely upon them saying, oh, I don't need to change anything, and that's going to work in this new environment. So what I've done, and what the people who are around me have done, is we've approached this in a kind of war college approach. Not to promote war, but to preserve peace. I like that one. That's the U.S. War College, the Army War College in Carlisle, Pennsylvania's motto. And I love this quote. I believe it's Churchill. I'm going to have to actually look it up. So we look at the new problem. Here's the problem on the network. Many networks, and I'm going to talk at first about non-switched environments, and then we'll go actually into the switched environments, because it's easier to understand if I take a few of the elements out of it to simplify what's going on. In a non-switched environment, so you're on a flat network. It's like the old party line. I mean, I know most of us aren't old enough to remember like the party line phone systems, but when I used to go visit my grandmother or my aunts, I'd sit there and I thought it was amazing that I could pick up the phone, and of course other people were on the line also. And she's like, oh, just, be a good neighbor and put the receiver down. Well, a lot of people decide not to be good neighbors, and of course you can sit there and listen in on all the conversations, even though it wasn't destined for you. In this situation, we have host A talking to host H. It's on a local segment. Maybe there are a couple of repeaters in there, maybe there are a couple of hubs. Big deal. They're, for all intents and purposes of this discussion, invisible devices. But I stress that because they are still stress points and weaknesses in your structure that you need to keep in mind. Obviously, B, C, D, E, F, and G can sit there and promiscuously listen in on this conversation if they care to. Now, the way they do that, I'm going to try and bring everybody up to a particular level before we really dive in and start looking at some of the packet structures and what's going on here, is your network card, or your NIC, your network interface card, has programmed into it a media access control, which is its unique 48-bit value. That is its identifier. It's not your IP address, it's your MAC address. It's watching things wing by the wire, and it's going to pick up only a few of them and hand it off to the operating system for processing. It doesn't want to hand everything off to the operating system, because every time it does, it's generating an interrupt, and the operating system has to actually take this data inside it, potentially do a context shift, and hand it over to user land, and then go back down into kernel space, and then wait for another interrupt coming over here. This is very overhead intensive. So the NIC, or the network card, is going to read the packet, look and see, is this my destination MAC address? And by the way, this is also why you see the destination MAC address come first in the Ethernet packet, so it doesn't have to do local storage on the actual card, looking for source then destination. You'll notice that it's flip-flopped in other parts of the protocols in the OSI model. If it's not for me, I just discard it. I don't need to tell the operating system about it. If it is for me, I'm going to hand it on over. Now, there are a few packets that are quote-unquote for me. One of them would obviously be the broadcast address on an ether, which would be all ones. One of them would be a multicast address, which would be the most significant byte, the least significant bit is set, meaning basically that the first number is going to end up being odd. And then there's obviously my MAC address. So Let's assume I'm in promiscuous mode and I'm saying, I don't care whether it's for me or not, I want to see a copy of all of it. And I'm sure most of us have played with these tools or more likely found some of them on our systems. I'm sure some of the people out here have put them on other people's systems. This was an old one from, this was using, we'll see if it was saying DevLE, that's got to be Lance Ethernet, so that's an old Sun system. And this was a standard. You see the Telnet option negotiation going on before, 255 being the IAC, so we see IAC do's, IAC don'ts. We see a username of BBS and a login of secret pass, and then the first command. This is just saying, hey, I'm reassembling the stream and I'm going to capture X number of bytes of the sessions going to port 23. You'll usually find these sitting in your /dev directory as a standard text file as opposed to a character or a block special device. So it's always fun to do once in a while a nice little sweep, doing a find, looking for non-block or character special devices in your device directory, and lo and behold, I guarantee if some of you go home, you will find sniffer logs there. Other ones that you'll end up seeing, because a lot of people instantly assume, oh, they're just sniffing for Telnet. So if I get rid of Telnet on my systems, then I'm all set. People are not going to find anything when they're sniffing. You might come across something and see this. Well, these are NFS handles. Of course, with the NFS handle, I no longer have to do any spoofing to actually authenticate, because the NFS daemon is assuming that the mount daemon actually was the one that I authenticated with and gave me the handle. If I already have the handle, I must have already gone through the authentication, so sure, give me whatever file access you want. This is less seldom found when you're looking for sniffer files, but it's a very important thing inside organizations that are heavily NFS-centric, which of course most people are going CIF-centric now, but there's similar problems over there. One of my personal favorites. But I don't have any static passwords going over. I've got challenge response stuff. I'm using Microsoft's shared message block for exchanging of the data. This we kind of ripped through with Loftcrack a long time ago. And you will see log files out here. I've seen several of them put on systems. I've seen them built for NT-style devices. Obviously, taking this information, you can plug it into a tool like that or Jack the Ripper. And then one of my personal favorites was if you actually logged on, or if you're sniffing the network and you watched 95 and 98 doing their file sharing, you'd notice that the challenge that was issued was constant. So you had the actual hash just by catching it. You didn't have to actually break it or crack it. So what else are you going to grab when you're on a machine on a local network and you're doing network sniffing? You're looking at the traffic. People aren't thinking so much about what the actual threat is. And this is part of the education on how to approach a problem. It's understanding what the real threat model is. The real threat model was not Telnet necessarily. That might be one component of it. The real threat model was not necessarily NFS. I might not have an NFS-based environment. The threat model can encompass a myriad of possibilities, but it's dependent upon your business. And this is one of the old school solutions not working in the new paradigm shift, is people are still looking for that silver bullet of, I've got a security solution and it's going to fit and work for everybody. Well, everybody's not the same, and everybody's business is largely completely different, and your threat models are different. So trying to pigeonhole people like that isn't going to quite work. I've got traffic and utilization times that I can look at. Maybe I want to actually launch the attack if I'm a malicious attacker during off hours, and I don't know necessarily where the systems are or what the office hours are for the people using them. Maybe I want to mask myself in extremely heavy traffic times, so I might do it during the middle of the day. I'll learn routes, systems, and topology of their local network. And as most of you know, I'm sure, this is more information than most of our IT organizations end up having for their own network. Recurring services or activities. These are the automated scripts that are running that everybody forgets about. And you start sniffing on your local network and you see this traffic going by and you don't realize it's, product X dumping its data over to a central server, or it's your security component that's deployed on all the different machines logging back saying what vulnerabilities that they have. Well, that's a nice data stream to go after. And it also tells you where they're sending that data point to, so you can just take over or direct your attacks on that one central server, and you have the entire organization, the entire company now. You know which ones are servers versus clients? And one of the ways that you might know this, not only just by looking at the direction and the bulk of data going back and forth, and this was one of our nice ways of looking for people who were doing reverse SSH tunnels backwards, even though it was encrypted, we could just watch for the amount of data that was going in a particular direction, and we could kind of figure out whether it was a reverse session setup or whether it was a standard forward session setup, because there's no traffic padding involved here. But also maybe through the DNS names. If I see DHCP 104 and it's 192.168.1.104, subsequently see the other DHCP names working, it's probably a client. If I see HR, dot whatever, if I see, recruiting dot or R&D, dot, foo.com, it's probably a server. And then obviously the static passwords, because why should you ever want to have to spend the time banging on the doors and setting off the bells and whistles and getting caught logging into a system when you can just grab the credentials from somebody else going by. So back onto the network side of things here. The two important parts we're going to look at here is the ether side, which is at the layer 2 of the OSI model, and the actual IP, the IP header, which is at the layer 3 of the OSI model. Over here on I put just for clarification, edification, the 4 layers as TCP/IP protocol suite looks. I'll refer to it throughout most of the talk as the OSI model instead, though. And we can see that we have the destination source address and the type. I'm not going to play with the type here too much, other than to leave, as I used to always hate in the technical papers, as an exercise to the reader. The notion of being able to address a machine with a legitimate MAC address, but playing with the type field such that you know that either the kernel discarded it at a particular time. It's a much more difficult latency attack to do, or it was actually going up for a user land area. This is one way of going through switches that might be configured correctly. I will caveat that, which I have never seen a switch that is configured correctly. So, and in the IP header, the important parts to us are going to be the source address and the destination address. And here's an example where you see that the source address comes first because we already know it's for the correct machine because, of course, layer 2 told us the correct MAC address, so we hand it on over. And, of course, in the OSI model, here's the disconnect. The data portion and the network portion. Layer 2 are the ether header, and the layer 3 are the IP packet in this particular case. So one of the methods that we first looked at, saying how will I actually determine if a machine is in promiscuous mode if I don't have an account on the system, so I can run ifconfig and see if it's got the promisc flag set, or even if I trust the ifconfig that it hasn't been rootkitted somehow for me, or that I trust that my kernel hasn't been completely compromised and I've got loadable kernel modules running around it. I'm going to have to sit there and somehow verify the integrity of a system that's already been compromised by trusting what that system that's been compromised is going to tell me its integrity is. Well, I don't. I'm going to be on a separate machine that hopefully I have better control over, and I want to touch it very slightly and exercise it and see how it responds from across the network. So we looked at DNS. And the first method, well, look, for those who don't understand what DNS is just the mapping of the the human readable name over to the IP address, because the computers could care less about what the human readable name is, but we're very bad at remembering extremely long and lengthy groups of numbers together. That's also why people are an extremely poor source of entropy, but that's a completely separate story. Yeah, if you get rid of the people out of the equation, this thing works great. So we have the hierarchical grouping of the domains, and of course it's necessary for the human convenience, and it gives away a lot of information about how we choose what we name things and the importance of them to us. So one of the first standard methods was we're going to send fictitious traffic across the network. We're going to then do our own sniffing. So if I'm sending a packet, and I see Professor Height over here, and Professor Height is being, a little naughty, and he's trying to sniff the conversations I'm having with other machines. And I'm sending a packet back and forth. It doesn't go anywhere. Nobody's going to pick it up. But I see Professor Height go, DNS server, who the heck is 192.168.1.1? I'm like, well, nobody should have known that one. So obviously he's in promiscuous mode. And you'd think, well, that's stupid for somebody to have left on reverse lookups in a sniffer that they've compromised the system on. But think back to, it's very telling. If I come back and I pick up, 5 megs, 10 megs, 20 megs worth of sniffer logs, it's going to be very important to the attacker to be able to quickly go through and figure out which machines are more likely the interesting ones to go after. I mean, obviously, other than looking for people that are logging with root over in clear text on Telnet, but, instant, freebie. If I see core-router-whatever, in there, that might be a little more interesting than DHCP 104, whatever. So this is method number 1. Method number 2 is something where we can actually send out little agents or clients out onto the other networks and send this fictitious traffic and look for people doing reverse lookups if we control the actual DNS server ourselves. The nice thing about this is that the DNS server can be located wherever we want under control, if it's in the organization. And we're just going to look for people querying our DNS server for machines that we don't have or that we have intentionally set the agents up to do these fictitious communications about. When the query comes in, we know that that system was compromised that actually asked for it. So we can have the DNS server across multiple switches. We can have it on different networks, so it can even go through routers. There's no problem here. And underneath we have the example of these fictitious machines 10.0.0.5 and 10.0.0.6 having a communication, which we, of course, have falsified over the network. I'll back up here for 1 second. The nice thing is I can force it to go, as you see, this is on a 192.168 network, and I'm doing bogus traffic communication between something that shouldn't exist on this network, unless you're like some of the large companies that are using everything as a transitory net, which I'd highly recommend against. So some of the pros and cons of the DNS method. Well, the pros are you can obviously work across multiple networks. One of the Now, the names of machines are very telling. Most people are leaving this reverse lookup on. If you're worried about people running EtherPeek or NetX-Ray or putting Data General or Network General sniffers on your systems, those aren't so much attack tools. And there are a couple of different ways that they can actually be set up. One is just statistics collecting. And when we initially came out with the proof of concept code for AnySniff, which is the free Unix stuff, people were going, well, it's not catching NetX-Ray. I was like, well, you're not really sniffing on NetX-Ray right now. Turn it on to actually grab the packets. You're just querying the driver and saying, how many packets have you seen gone by? You've got the little gauge meter going. I'm not worried if somebody's on my network going, maybe I should be, how much traffic utilization am I having, but they're not actually grabbing the packets. It is a threat, but it's a different threat model that I'm not trying to approach right here. It doesn't saturate the local network. This is very important because we're going to show some examples that completely lay waste to your network in order to figure out who the actual ones are in promiscuous mode. Yeah. And then finally, the high reliability. You have very minimal false positives. If I just sent out a communication between fictitious hosts and somebody asked who the heck these hosts were that was talking, and it wasn't destined for them, I'm pretty positive that person was listening to a conversation they shouldn't have been. Obviously, the cons are you don't have to have reverse lookups going. And if you don't have the reverse lookups on the sniffing things, this isn't going to do you squat. The other thing is that I might want to run it, and I'll send out information across the network now, and I'll look for the response within the next 5 seconds or so. But it might be that somebody goes in to collect their data, grabs that 5 megabyte file, and then runs a batch reverse lookup all at one time. I might not be actually looking for these responses at that moment. The other fun ones, and it's always wonderful to be able to look at a problem and say, theoretically, this thing should be wonderful, but in practical use, this is going to be rather painful, and you can see where people are going to take shortcuts. And if you can kind of understand how people think when they're creating things and designing things, you're way off on the War College front of understanding how to break them or how somebody else is going to break them. So Some of these, all of these are actually just implementation problems, but they were such widespread implementation problems in stacks of major operating systems like Windows NT, like Linux and the BSD trees that, it worked. And again, you don't have to have 100%, accuracy all the time. If you're hitting 90%, you're well above the curve. What we're going to take advantage of here is when my legitimate machine's MAC address for the actual NIC does not match what I've bound the interface adapter to on my IP stack. So if I'm 192.168.1.10 and we see I have 080020, which is obviously a Sun system by the first 3 octets, and somebody else sends a packet across the network with all 6s for the Ether MAC address, but with my IP address, if I'm not in promiscuous mode, my network card is just going to look at because remember, it's just looking at the Ether header. It's going to look at that and say, that ain't for me, and ditch it out of there. If I'm telling the network card to be in promiscuous mode and give me a copy of everything that you see, did I correctly do this such that it's not saying, oh, that IP address was for me, and incorrectly in this case, actually hands it to the stack as opposed to just sitting there in user space, or whatever the application was saying, I want a copy of the data that you're receiving, this is for debug purposes. You'll notice that on the Ether address here, we chose all 6s, and this isn't some sort of demonic or satanic thing. What it is this is an invalid MAC address that is not multicast. We learned this the hard way. If you start sending out all sorts of crazy stuff in multicast addresses, your network's going to be in for a world of hurt really quickly. This was very bad because at the time I was living on an extremely populated Class B. People were not happy. Government people with guns were not happy. I was tickled pink. Anyway, so the first test is Linux had this classic example. I would send, if it was a non-promiscuous mode, this is normal behavior. Let's say it's something that I'm almost always going to guarantee that I elicit a response for. ICMP echo request, wonderful example. Maybe it's even something where I could send like a UDP packet to a port that isn't listening, so I'm going to try and listen then for an ICMP port unreachable. Maybe I can take advantage of, if I scan the system first, that it has other components on it. Maybe it's running the old echo command, so I can hit it on TCP or UDP there. Well, in normal behavior, I send it the packet, I've got the correct Ether address, I've got the correct IP address, and it sends me a response back. All is well in Joyville. And here we have, if I send it with the incorrect Ether address, of course, it's never going to be handed over to the system, and as such, I'm not going to get any response back. But lo and behold, on Linux's stack, and this has been fixed, but obviously saying this has been fixed still means that about 99% of the entire internet out there is vulnerable, even if it was fixed about a year ago. I send the packet out. The NIC passed all the traffic to the OS, and the OS forgot to check the MAC address and was only looking at the IP and said, oh, this is actually for me. I'm doing the filtering here for the switching on which direction I'm going to actually fork the packet off to. And it handed up the stack, and I got a response. Well, can anybody think of a real quick way, well, let's go back to that wonderful Class B network, sending out just a few packets and nailing everybody? Broadcast address of what? Of the Ether or of the IP? Well, if I send out the broadcast address of the Ether, and let me restate what was said. People correctly said the broadcast address, and I wanted further clarification on whether that was broadcast Ether or broadcast IP. The statement that either would work isn't necessarily true, but you're on the right track there. If I send it out to the broadcast Ether address, and I don't have the correct IP address in it, well, everybody's going to listen to the broadcast Ether. But they're not necessarily going to operate on it because they're going to go, that really wasn't for me. I can show you some neat tricks with broadcast Ether for sniffing anything you want in a switched environment, and then getting it back out, man-in-the-middle style. But that's a separate thing. If I sent it out with the broadcast Ether and the correct IP address, of course it would respond, and maybe it was broadcast, the IP address, everybody would respond to me. They didn't care. Now, if I send it out with that bogus 666 Ether address or something else that's not a legitimate MAC address, but the broadcast IP address, all of the Linux boxes on this flat Class B that are running the older kernel are going to sit there and respond back to me, and boom, I instantly know like 10 or 15 or 20 systems that are in promiscuous mode. The nice part about this is that when they're in promiscuous mode in this fashion, I don't care whether they're actually sucking the packets down or anything. All I care is that that promiscuous flag has been set. So they might not be doing anything wrong, but it was always wonderful fun to be able to pick up the phone, after I looked up and saw whose machine it was, and call them up and say, "Why are you sniffing the network?" I'm like, or they'd be like, "I'm not sniffing the network." It's like, uh-oh. Yes, you are. We've got a problem. This didn't work on BSD, but something else did. What we would do, because of course I was sitting there looking at it saying, hey, I want to hit this broadcast address. I wanted to minimize my effort. I didn't want to have to map this entire Class B or worry about multiple Class Cs and go out every single time. I wanted to just send a few packets out. I'm lazy that way. And I wanted to get the responses back. So I said, nope, I'm going to hit the broadcast. And sure enough, while it didn't work on BSD for the direct unicast address of the IP, if I hit the broadcast IP, it demonstrated the exact same results. This has also been fixed. But I couldn't understand what it was when I was calling up saying, oh, you got a Linux box that's in promiscuous mode. And they're like, no, I don't. I've got a NetBSD box that's in promiscuous mode, you schmuck. So, of course, I didn't want MT to get away scot-free. So it's hey, they want to play in the same ballpark. They're going to play the same ball game now. We looked at this one. This was really neat because this shows, and this is a great example of how people, if you think like people, you can understand what to go after. And it's very easy to do a comparison of a word because a word is 4 bytes, and you can just say hey, I've got pick an int or something that's actually going to be a word on your particular machine. I can just compare these two things. Well, there aren't many structures that are 6 bytes long that I can do a direct comparison on. But broadcast ether is 6 bytes of all ones. So you see all the F's down here. I can do this comparison byte by byte, but that's going to be relatively slow. Normally, when the hardware is doing this, it has this built in, and it's going to look at it in the custom ASIC or the actual network chip, and it's going to do this comparison for you. It's not even going to bother the operating system. But I want the operating system, if I'm in promiscuous mode, not to have to spend time doing a care-by-care type comparison here. I want to just say, do these two match? If so, hand it in. If not, discard it. So what I'd do is, I'd look at the first four bytes. I'd compare the word. I wouldn't care about the last 2 bytes. Well, 4 bytes of ones and then 2 bytes of zeros is not ether broadcast. But for most of the Windows systems, and this was in their sample driver, the default one that most other vendors making network cards wrote to, they'd only compare against that. And if they were in promiscuous mode, they thought that was broadcast ether. So I could send out an ICMP echo request with the ether address of FFFFFFF0000, and the NT machines that were in promiscuous mode would respond back to me. And of course, if they weren't in promiscuous mode, they'd do the entire comparison, and they'd say, I don't know who the heck that's for. Maybe it's multicast. It's definitely something. So the ether tricks, the pros and cons. You've got a really high reliability because you have very small false positives. I'm not worrying about what we're going to see shortly, which are some of the latencies attacks, and the time deltas. The shortcomings, again, are you're limited to the local segment that you're on. What happens when, well, I say that, and of course I ran this on my local, I had a DSL link for a little while recently, and I decided to tweak around and come out with a Linux port for anti-sniff, kind of for giggles. Released it out. I wanted to test it. So I'm on my little local DSL. I got a little network at the house, and I say, well, I'm just going to broadcast it out. What do you think happened when I sent out the ether packet with all 6s? Well, much like any switched environment, which is why I kind of stopped myself there saying limited to the local ether segment, it's usually limited to the local ether segment. A lot of switches, if they don't understand where a machine is, and they've got these spanning tree topography or topology maps, if they don't know where an end node exists, they'll flood it out. They turn into basically bridge mode. And since 66666666 whatever doesn't exist, it's going to bridge that every single time. Now, smarter ones will actually learn and say, I will flood it once, And if I don't get a response, I'm not going to update and do my new spanning tree telling everybody where this lives, and I just won't send that thing off again. But most of them aren't smart. Most of them are dumb. I'm telling myself a funny joke that I haven't heard before. I'm losing it. All of a sudden I found everybody on this particular DSL provider's network that had a Linux box that had been compromised or that was intentionally trying to sniff local networks, because they started responding to me. I was amazed at this. Normally it'll stay on your own local network because the ether address isn't going to go out. It's not destined to the router, and it's not a packet that's not originally to the router, so it's not going to be forwarded. And if you're in a switched environment, most likely the switches are actually going to stop it. And the other con, of course, is that it's very dependent upon a particular nuance in an operating system. Now, I would argue that this particular nuance in the operating system, isn't so much of a bug as it is something that's beneficial to us. This is one of those, it's not a bug, it's a feature type statements. Of course, vendors will fix this, and this is one way you're not going to be able to tell that machines are in promiscuous mode. I don't see the disadvantage to some of these problems right now, other than the fact that it definitely shows that people are doing humanistic coding qualities or coding traits, meaning lazy and flawed. But then again, we are humans. The machine latency. This is one that I was listening to Tom Patachek probably about 3 o'clock in the morning after many, many beers, and he was going on about some argument that he was going back and forth with on comp security or risks, or I forget which mailing list was, but I was absolutely enthralled by it. It's a very simplistic test, and it should work, but he hadn't been able to get it to work, or else he hadn't really experimented with it. He was just theorizing and hypothesizing on it. I wish I could take credit for doing this, but this is, to my knowledge, Patachek's and Pindusham, I think, was also involved with that. It's been what it's doing is it's saying, look, when I'm not in promiscuous mode, my hardware is going to do the filtering for me. And my hardware is pretty quick and pretty good at it. My hardware doesn't bother me too often unless it's something that I really need to look at. Now, when I'm not in promiscuous mode, or when I am in promiscuous mode, I've told the hardware to turn off all of its nice filtering. Give me everything. I want it all. And the software stuff is not that fast. Why? Because it's the operating system itself that has to generate all these interrupts. On top of that, I'm probably a user space process that is doing this, and I'm incurring a context shift from user to kernel space every time that I'm having it hand me over this data. That's very expensive. So, the theory goes like this. If I hand out a whole slew of traffic that's not destined to anybody, and at the same time on this local network, and I pick somebody on the local network, and I start to ping them, or I start to get a latency measurement on their response time, it will be at a particular value. Now, I also get this latency measurement of the response time when I'm not sending any traffic across the network. So I've got a clean one, and let's say it's 3 milliseconds, and I've got one where I'm flooding the network with traffic not to this host, and then I get the latency at the same time, and that's maybe 5 milliseconds. I'm just picking numbers out of my lower abdominal area. But we saw it increase. Does that mean it's promiscuous mode? No, not with that small of an increase. That's standard overhead. I mean, the card does have to do a little bit more. It's going to hand it over. It could be that there was something going on the actual operating system. Maybe somebody was doing a compilation. Maybe somebody was doing something that it just happened to do a few context shifts and incurred extra overhead, and as such, my latency increased. I've seen them go actually both ways during that, where I'm sending nothing out on the network, and when I flood the network, I get a faster response time. Now, if this machine was in promiscuous mode and making a copy of all of these packets that I was flooding the network with, what do you think happens to the latency time? I'm going to see a change from about 3 milliseconds up to about 300 or 500 or 1,000 milliseconds. This is a noticeable increase. This tells me that something is amiss on the system. We decided to take these ideas and really start to fine-tune them. and figure out how could we exacerbate certain problems and minimize the discrepancies in others. So we'll walk you through some of the actual examples and little block diagrams here. So we map out A, B, and C with their ether addresses. And of course, I made them all sandboxes, so this is unhappy. To particular IP addresses on one of the Class C reserve nets. We'll see in the beginning, we send over the ICMP echo request. And keep in mind, it doesn't have to be a ping. It could be anything else that you can elicit some sort of time response back. But the nice part about the ping is that I can put into the way the echo request works is I send it the packet, and it sends me back the same packet that I sent. This is how you're getting these time deltas in it, because you put the local time of your system in the packet, send it over, it sends it back, and now I can compare my current local time to the packet that I got in the received response. That by itself doesn't work tremendously well, but since I can control what I put in this ICMP packet, I'm going to put an extremely high-resolution timer in it. I really want to be able to nail this down. Now, some of the operating systems didn't have high-resolution timers, so we kind of, built into the OS, but the hardware did, so we kind of like tapped in various ways. Can you think of any way of defeating this right off the bat? And of course, when you're looking at problems like this is one particular solution to a threat model. Now, I have just introduced a new threat model to the person who's sniffing. So, of course, they need to react and act on this if they're going to try and stay one ahead. It becomes an arms race. One of the ways that, Bill and myself and some other folks inside the R&D labs were playing around with is I'd sit there and launch this thing out, and he'd send the packet back, but of course he replaced the value inside the ICMP packet. So I was getting like negative response times from him. I mean, Dill's good, but geez. Other mechanisms are, of course, I might want to actually watch when somebody starts flooding the network, and I can just have something that periodically turns the card into promiscuous mode to see if I'm getting such a spiked level of network utilization. I'm going to turn the sniffer right back off. And this was a clever one. I liked that. This is not a be-all, end-all. Again, we don't have to go for 100%. Anyway, I see that I've got a latency of 2 milliseconds on a machine that might or might not be sniffing, and I've got a latency of 3 milliseconds on a machine that might or might not be sniffing. I now flood the network with ICMP packets going to a separate host that doesn't exist with bogus ether source and ether destination addresses. And again, you don't have to choose the all sixes. It's just nice because it doesn't turn the multicast and set off alarms. And I'm going to watch that the latency went up to about 4 milliseconds, fine, most likely not sniffing, and 300 milliseconds on machine B. Well, machine B was probably sniffing, and in most cases, machine B there was sniffing. But once in a while, these machines, and I haven't figured out for the love of God why, or whichever minor deity that you actually bow down to, some of them were the exact opposite. Some of them would be up at these extremely high latencies when they're not sniffing, and they'd be at extremely low latencies when they were. So, what's the solution to that? The solution, we said, well, it's still a change. It's still a delta. So, in a perfect world, what you'd like to do is make a baseline of all your systems. And if I have a baseline of my systems and I see that one is normally, when I'm flooding the network very fast and when I'm not flooding the network very slow, that's fine. That's their baseline. If I see them switch, well, something changed on their configuration. They probably went into promiscuous mode, and this ended up working quite well. Of course, it obviously worked for the ones that were giving a small response time that instantly jumped up. That's the model that we were expecting to see. One of the other comments that people were saying is, well, this works great for detecting machines on the network that are in promiscuous mode that are addressable, that have an IP address. Well, yes, that's what it was designed for. The person who's breaking into your R&D server or your web server is probably going to attack its IP address if they're over on the network. If they're coming in and sitting down at the terminal, you have a different threat model that you need to evaluate. And if they're bringing in somebody else, well, I can bring in, I can clip the leads off of the wires, or I can take the network general's dedicated sniffer box and put it up in the acoustic ceiling tiles. You definitely have a different threat model if people are walking around your offices doing that. There are certain ways that you can still tell if a machine that doesn't have an IP address bound to its interface is sniffing. Let's say it's an intrusion detection system. Now, most intrusion detection systems are not configured poorly enough such that they have one interface and it's doing the sniffing and the management. Some of them do. I'm sure we've all toyed around with personal ones or little test environments that way. But a nicer way to do it is to actually set up interfaces on the different networks so you can attach to multiple ones. If-config them such that they don't have an IP address bound to them, and be very careful when you if-config with all zeros on some, because some of them that actually binds all zeros to it, which was the old broadcast address. But setting up these non-addressable interfaces and then having a back-end network attached where you can do your querying, do your polling. As long as I have collusion with another machine, and in this case, I've got host A who's flooding on the network, on this 172.16 network that B, which is the intrusion detection system, is monitoring on. Of course, nobody can touch interface 2, which is that network drop. Doesn't matter. I'm still introducing extra load, especially in an intrusion detection system, which is going to do what? Reassembly. It's going to try and do statefulness. It's going to, if it's got any chutzpah at all, it's going to try and check the checksums on top of the packets. It's going to try and look for time to lives that are exceedingly varying very quickly back and forth. So that might be a method for evasion of the intrusion detection system. And I'm on C. If I know where the address is, the addressable management port, I'm going to see this exact same latency change. Sure, I might not know which other networks to hit on, but then again, if my organization has 5 networks, sure I do. I've got one network and then 4 others, and then I've got one network and then I've got 4 others, and I do that 5 times and I've hit all the combinations. So, we weren't getting great responses, and I thought, damn, this is probably what Patachik ran into. Patrick, I'm going to probably butcher his name forever. He'll give me a phone call, I'm sure. And Newsham were probably having problems with, and I don't know whether that was or wasn't. But we looked at it and said, well, again, what's our threat model? Our threat model is somebody who's sitting there looking for TCP connections most of the time. We were worried about people who were putting in the standard Ethersniff, looking for Telnet, looking for SNMP, looking for static passwords. And geez, once you start thinking about how many static passwords are going on the network, it's absolutely terrifying. IMAP, POP, Outlook, type stuff. You've got NFS for the file handles. You've got 9598 SMB stuff. You've got attackable ones, which are SKey. That's a challenge response, but it's still based off of one static password. That was chosen most likely by users, and of course, users are poor sources of entropy. All over the place. Well, we said, how do we exercise the system the most? If somebody's looking for a TCP connection, and I just start flooding ether packets that are all 6s, I'm just taking, I'm malloching a big chunk of memory, filling it with 6s, and just shoving it out the network tap, guess what? That software, even on the user space side, or the user land, is not going to process it tremendously. It's going to say, nah, it wasn't for me. They might even have pushed down like a BPF filter of some sort. So they've got still some kernel module filtering or kernel level filtering, even though they've lost the hardware component to it. So, well, we control these packets we're setting out there. We fake up entire 3-way handshakes. Sin, ac, ac. And then we might even start sending further data inside of that. So that it says, oh, I've got this. I'm going to start reassembling it. That matches my criteria. I'm now entrenched in the user program. I have matched the criteria for my BPF filter, for my libpcat filter, my VLPI filter. I might just send a whole bunch of sins. This was another way we figured out how to turn off most sniffing programs, most malicious ones. You could turn off Ethersniff, you could turn off EtherPeek, NetX-Ray, just about anybody, TCP dump, Snoop, by sending in malformed packets. So it was kind of humorous to say, I'm going to search the network real quickly, find out who's in promiscuous mode, and then maybe even offer you the option of turning it off. Again, some people were not happy when we started doing this on this large Class B network, but this was in a different day and a different time. Some of them had legitimate research reasons for being in those states. So they told us after. What else? The pros and cons for this. One of the huge pros is it's cross-platform. I don't care whether you're a Coke machine running on a BASIC stamp I don't care if you're an NT box, an OpenBSD box, a NetBSD, a FreeBSD, a Solaris, an HP UX box, you name it. I'm looking for almost, again, a general. One of the other pros is it often crashes the sniffing programs, which, as we learned, sometimes could be down under, I should have put that also under cons. It is confined to the local segment, unless your switches are really brain dead, which many of them are. Which is also one of the cons, that it's limited to the local ether segment. And if you're looking for the shift, it's got very high accuracy. And when I mean the shift is when I see a machine go and I've baselined it and it's responding at 300 milliseconds and it goes down to 3, or vice versa from 3 up to 300, that's a pretty good signature. It would help me more if I could gauge the current level of network traffic, such that I know if I'm generating extra traffic, I'm just creating collisions and I'm really not increasing the overall traffic load. I just think I am. I'm giving myself this illusion of exercising the network. Cons, of course, of the network congestion. It oftentimes crashes switches. It's also one of the pros. And you really do have to make assumptions that the end node, geez, I'm going to call up and I'm going to run after this person, and they weren't in promiscuous mode. It just so happened that when I did the delta without flooding the network, the guy was taking a sip of coffee. When I started flooding the network, he hit return and he's forked off 13 instances of a global make file, on a huge project, instantly introducing tremendous amounts of latency on the system. And then, of course, you have to think, well, this was a fun little exercise. It was, I want to find beforehand. I don't want to find by looking around in the system. I want to find a new solution to a common problem. This is how you approach the paradigm shift. I want to have my own war college. We heard Richard Thiem talk, and it's kind of humorous because I had been espousing this for a little while. I was down in Texas speaking with the SPA War folks and a bunch of other Navy underwater warfare muckety-mucks and military folks. And I said, here's the problem. You're looking at it from remediation. You're looking at it in a tactical solution. You're not approaching this strategically. You're not saying, I'm going to figure out how to break the damn thing myself. I'm using this stuff. I'm relying upon it. I'm going to beat the hell out of my own war college. I'm going to find the attack. Okay, bad side effect. I now know a new attack that the rest of the world doesn't know. I don't think that's necessarily a bad side effect, because you get to actually fix the problem before it's found somewhere else. And since you found it, or you might not have been the first person to find it, but you're the first person to hopefully make it public, you control the spin and the slant and the angle of releasing this information. If I release something saying, here's a program that'll crash the internet because it's basically a distributed denial of service attack, well, I've kind of slanted you over towards a negative use of this tool. But if I release something and I say, here's a problem that we see, these are some solutions, and this is how it works, I've actually done some research here, and I haven't slanted it towards the negative side. If I think about it for a while, I can even figure out a really nice positive way to slant this information and release it. This is kind of like if we gave out hammers to everybody. This was something that Marcus and I were talking about yesterday in the little panel. If I gave out hammers to everybody in this room, most people would probably do something benign with them. If we gave out guns to everybody in this room, paintball guns, I guarantee you 30 or 40 of us would be covered with paintballs by the time we walked out that door. They're both tools, and they're both capable of a few things. One has been pitched to the general public with a building and constructive and creative and beneficial use, and one has been pitched to the general public as an antagonistic, offensive weapon. Guarantee you I'd rather be hit by a paintball than over the head with one of the hammers that we handed out. So, anyway, I just, rat holed down that one. That's absolutely fine. The Richard Thiem thing. He was talking about these companies being non-bound to particular nations, particular, political places. You've got these ubiquitous organizations that exist worldwide. And guess what? They're deploying infrastructures that are huge. They're using these huge switches. They're using these huge routers. They're trying to model traffic in volumes that have never been done before. Well, they have the opportunity to create their own war colleges inside of these organizations. And this scares the bejesus out of the military, because the military can't really get away with saying, yes, we're trying to write the next virus to figure out how to defend against it before it exists. That scares the people, because our government really is, gets a black eye when they say that we're engaged in offensive warfare studying tactics. We are. We'd be stupid if we weren't. But an organization or a corporation can get away with saying that with much less reciprocity or fear of. So, by thinking of this in the war college analogy, having it inside your organization, or hiring a going out to a war college for hire, if you will. What are some other ways we could try and spot the curious or catch the sniffer? Well, let's create fictitious connections to, a real machine, a bogus account that doesn't exist, and watch the log files on this machine in case somebody actually did log in on it. If somebody logged in using this, guaranteed they were watching information that they shouldn't have been seeing. This is just kind of a further elaboration on the DNS lookup. This is the trap account. And I'm sure if we put it to people in this area, we could think of a whole slew of possibilities like this. This is the forward thinking. This is the teaching people how to think. I'm always very concerned when I come to these conferences, because I'm going to go to the talks and people are going to be saying, I need to react faster. I need to be able to get the information as soon as it's available. And they're waiting for somebody else to find the problem, and they're always playing catch-up. And this is security in the catch-up role. And security loses that way. It doesn't scale. But if you look at it and you try and find it yourself, and then you share the information before it exists, well, this is how security becomes an enabler and allows you to do things in a company or a corporation that hitherto, that previously you were afraid to because of the risks associated with it. That's the talk. What I'm going to do is, after we break for the deep knowledge session, I'll field a bunch of question and answers there, and I'll run through and I'll show a few of the graphs to show the different spikes on the latency analysis. So, thank you very much.